First of all, thank you very much for inviting me to talk about static resource analysis at scale with Infer. My name is Ezgi Çiçek and I'm a software engineer at Facebook Static Analysis team. This work is in collaboration with my colleagues Sankun, Dino, and Mehdi, who was at Facebook previously. Okay, let's dive right in and start with how performance regressions are detected in big code bases in the industry. Initially, whenever a developer sends a code change in such systems, it is submitted to the CI system, which runs some tests and type checks the program, and then the code modification is sent to a code reviewing system. For instance, Fabricator, where reviewers take a look at the code and they either ask for modifications or clarifications, which in this case the code goes back to the developer, or they approve it, and once approved, the code goes through again the CI system where some more tests are run, and finally, if everything is okay, it lands in the product. Here, there are several points where perf regressions could be detected. Before submitting the code via these continuous integration testing systems that test the program whether the performance has been okay or not, or afterwards via monitoring the resource usage of the program. And because only a limited amount of testing can be done before the code is pushed, by the time a regression is detected, it is often too late. The poor user is already going down the hill, and perf engineers are at the top of the hill and wondering what happened. And this type of phenomenon is not only limited to the execution cost of a program, but also to other type of resources such as memory or network behavior, where it might turn out that there has been some regressions in the resource usage of the program much later than the ideal case. What is next? Well, now performance engineers need to figure out the root cause of the issue, which might be difficult, since in a big code base there are thousands of commits every day, and they would have to find the root cause in so many commits. It's like finding a needle in the haystack. Okay, once they found the root cause, let's assume this is done, then they have to decide what to do with it. Revert the issue quickly to prevent any more damage to the user, or try to fix it. Once this is decided, finally, now they need to ensure and double check that the fix really improves the performance. And as you might imagine, this whole process of identifying and fixing the performance regressions is costly not only for the application and its users, but also in terms of engineering time. In fact, it requires multiple developers to interact and coordinate and may take days or even weeks. What makes performance different than other type of bugs? When we look at the typical functions correctness pyramid, we see that there are many ways to find out if there are bugs that cause the program to crash or to produce an unintended result. At the bottom here, we have types that are the first protection level for preventing unintended behaviors, such as simply adding one to a list or more complicated ones. Then we have linters that catch many trivial and syntactic issues, but they are usually very shallow. In addition to types and linters, we have static analysis tools that catch more sophisticated issues by symbolically analyzing the program, that is, without running it. So on top of these static techniques, we have various dynamic techniques that range from unit to end-to-end tests, which require us to run the program either fully or partially. And as you can imagine, as we go up the pyramid, we are relying on more dynamic techniques, which are expensive and slow. Moreover, tests can only uncover issues in some execution paths, but not all. And in a big code base with very frequent code changes, it is also not practical to run all these tests for each code change. Therefore, it makes sense to dedicate more effort at the bottom of the pyramid, where static analysis techniques shine with their ability to reason about all execution paths statically and provide a much more quick feedback compared to dynamic techniques like testing. But when we look at performance, we see that at the bottom, there is almost nothing being used in big code bases. For instance, when we look at types, we see that convincing developers to even use conventional type languages are a big effort, let alone convincing them to use the sophisticated resource types. What about linters? Well, we can see that there are some performance-specific linters out there, but they are very syntactic, hence shallow, so they do not provide enough capability to catch performance issues. What about static analysis? Luckily, there has been lots of research in static resource analysis. Perhaps the most famous in this line is the work of static worst-case execution time analysis used in validation and certification of embedded systems in safety-critical settings like aviation or trains. To estimate real-time bounds, these analyses must be tuned carefully to take into account abstract models of caching, scheduling, and pipeline behavior of the embedded system, which are unlikely to be possible in a big codebase where there's an ever-changing ecosystem of hardware and scheduling under the hood. But general ideas based on abstract interpretation are still useful. Another approach, which is perhaps more general, is type systems, which are more abstract but require designing type checking and inference algorithms per language. And often these type of type systems might require resource annotations on the program and may require sophisticated backends to SMT solvers. Well, good luck convincing developers to do that. So finally, the more hardcore version is program logics, which require proof engineers to dive into the code and craft proofs with proof assistants like Cog or Agda for small code bases. And as you might imagine, this might be difficult to scale up to big code bases without dedicated effort. That brings us to the main aim of this talk. In our work, our aim is to take the ideas from static resource analysis research and apply it to big code bases. And by doing that, we shift the focus from program proofs to bringing value to the developer before code is shipped. So if we go back to the diagram of lifecycle of code changes here, our aim is to be a static control point here, warning the developers that, hey, there might be a performance issue with their code, hereby pushing the verification effort to the left as much as possible where it's cheaper and more scalable. And how does our analysis work? In a nutshell, the analysis is based on an abstract interpretation technique which computes symbolic upper bounds on the resource usage of programs. In particular, we rely on Infer's static analysis framework. For those who are unfamiliar with it, Infer is an open source static analyzer which provides a framework for writing interprocedural analysis and linters. And Infer has support for Java and C family of languages. Infer's architecture is similar to that of a compiler. Language frontends translate the program into an intermediate language along with the control flow graph of the program. And then backends do all the magic on this same intermediate language to compute different type of analysis results, like null pointer exceptions, resource analysis, which I will explain you, and many more analysis like use after lifetime that you might have heard from incorrectness logic recently coming out, and then RacerD for concurrency analysis. Let me briefly explain how the analysis works with a simple example that loops over a given parameter k. Infer will take this program and translate it into its own intermediate language along with the control flow graph. So if you look at it here, for instance, the node 4 here will be assignment into I, 0, and then we will have the prune nodes which will decide whether we stay in the loop, that is I less than k, then we stay in the loop, otherwise we exit the loop. Now, if we start with a node, the execution cost of a node will depend on the execution cost of its instructions. So for instance, in this node here, we can have a very simple model and say that execution cost of a primitive instruction will be unit cost. And then it will be number of times this node is executed, all right? And for straight line programs, that's trivial. For in this case will be, for instance, 1. Or similarly, start and end nodes will also be executed once. But for others, the control flow graph implies inequality constraints on how many times each node is executed. A node is executed at most as much as the sum of its predecessors, that is the incoming edges, and as much as the sum of its successors. These result in constraints. Then combining these with Infer's abstract interpretation framework and taking the control flow into account, which result in these constraints, we derive a symbolic polynomial for the execution cost of the function. So in this particular case, we will get a cost 5k plus 6, which will be linear in the size of k, which was a parameter to the program. And also let me point out that the way we account costs for primitive operations could be adjusted. So rather than executing unit costs for each primitive operations, we could change our underlying cost model and account different costs for different instructions. Or for some instructions, we could say we incur zero cost. That is all possible to be adjusted according to what type of resource we want to account costs for. So the model is very generic. To see how many times a node is executed, for instance, let's take a look at this program. And we start here from an observation that assuming termination, at each iteration in the loop, we should reach a new state. Thus, if we can bound the number of states that are reachable at a program point A, then this number provides an upper bound on the number of loop iterations. So to determine the number of different states at each node, we first identify a set of control variables. These are variables that can potentially influence the exit conditions of the loops. So for instance, it will be I and J. And then we identify variables whose values stay the same in the loops. So for instance, instead of 5 here, if we had 5 plus k, then k would be an invariant variable because its value doesn't change, whereas I and j's values would be changing. To do that in general, we would need a pretty analysis that would tell us also the results of which values are invariant. Once we do that, then we compute the size of the state at each node by computing the product of the size of these variables. To determine this, that is the set of values a variable can take here, we rely on interval, which is a numerical interval analysis that will tell us, for instance, for I, the values I can take will be between 0 and 4. So 5 values. Similarly for j, it will tell us the values j can take will be between 0 and inclusive 9. So 10 values in total. So then we can say that the loop A will be executed by 5 times 10. So this is for loops. What about function calls? Here, if we have this same program loop and call it inside with a value x, whose values range from 0 to x, which we can get from Inferbo's interval analysis. Assuming that, then we can conclude that this program's execution cost will be constant. To do that, we look at for loop summary. That means we don't rerun the analysis for loop, we just look it up from the already computed summary, which said that 5k plus 6, then we substitute a constant value for the variables x can take, then we conclude that this program will have a constant code. Note that here we are not rerunning the analysis on the loop, which makes it scalable by looking it up from the existing results. Next, if we had to call loop with, for instance, two parameters m and n, and call it by loop m times n, then we would get, for instance, a quadratic bound. Again, relying on loop summary. So this concludes my summary of how the analysis works. Let's see how we could deploy this in a big code base. Well, the first idea could be that, well, let's try to deploy this running it at nighttime every day and compare the complexities of the modified functions. So one approach would be like to do a batch deployment, nightly runs, and then see if there has been regressions between the execution cost of a function. But by the time we might find this regression here, it might be already too late. Code could have been already landed and affected the users. Secondly, developers may have already moved on to do different things. We can't expect them to context switch from what they are doing to show them with a new issue with a complexity increase. At the end, developers just want to write code. They have no time for an issue from 2 days ago they already forgot about. Instead, a more developer-friendly approach is to do diff-based deployments, where we integrate into the code reviewing system and act as another code reviewer and tell the developers that there is a complexity increase in their code. And this way, we don't block the developer, but our analysis needs to be quite fast, which is thanks to our compositional and modular approach of reusing summaries, we can do that and report under a reasonable time. So to show you an example, let's look at this code of cancel. You don't need to read the details of the code here, but here the developer removes this implementation and instead adds a new function which calls into another function which is iterating over a map. And then here, if you were to run infer on this, infer would report that, okay, previously infer found out that the complexity of cancel was constant, and now the complexity increased here. So infer would comment here just like a normal reviewer and say that there might be a complexity increase here. Complexity increase from O1 to the size of the map. Please make sure this is an expected change. And here we are only reporting when the warning is introduced by the diff and only in files changed by the diff. That means if a function cancel is being called somewhere else up in the call stack chain, we wouldn't report there because we don't want to annoy the developer at all these call stacks, which might be a lot and have a knock-on effect in a standard integration. And moreover, developers to understand this complexity increase, we also allow them to look at the traces to understand how the complexity increased here. Developers can interactively play with the trace and go through, okay, cancel for calls this and this calls that, and then explaining for each symbol and navigatable link on call stack information, along with the cost for each function call. This analysis has been running on Facebook's Android codebase for more than 1.5 years, and recently we enabled a new integration for its Objective-C codebase. Each month we are running over thousands of diffs, and we are catching hundreds of complexity increase issues. I want to briefly share a few anecdotes and reception we get from developers. Most of them are surprised that Infer can automatically do such an asymptotic analysis. For instance, they say, oh, this is cool, I didn't know it did this. Or they could look at the issue and say, wow, yeah, actually this made me reconsider the methods I was using and ultimately choose a better approach. Next, let me dive into a few challenges and opportunities to improve things. So first of all, some technical challenges. First things first, there are some things that we do not handle, like recursion, which we believe doesn't occur very often in conventional code bases. Might be surprising, but true. Secondly, we assume a sequential model, so we do not take any of the concurrency into account. This is a limitation of our analysis, but a future opportunity to make things better. Thirdly, to work well in a big codebase, we need models for many of the library codes. For instance, here, if we don't know the range of values for foo's result, then we can't determine a bound on the number of times this loop will be executed. Therefore, to give a precise bound, we would require a semantic model for foo's results. For example, if foo is a library function which always returns a constant, then we could incorporate it into our analysis. Then we would say that this program, this loop, will be executing in constant time. But we also need to know how much time foo takes. So even though it might be returning a constant, it could be that it does that in a linear time. So we need two types of models here. One for ranges of values and one for costs of unknown library costs. Fourthly, intervals inferred by inferbo are limited to affine expressions, not polynomials. So we can't get bounds like square root of x. Again, this doesn't happen very often, but worth to point out. So these were technical challenges. Next, let's look at some domain-specific challenges. First of all, one thing that you have seen in this talk that might be in your mind is that, well, complexity increase here could be intended or even expected. It might be telling the developer that, hey, caution, there's water on the road during rain. Well, to deal with these, we ask the developers to provide us some feedback. They could tell us, oh, this is good catch, or it's expected, and we could improve our analysis based on that. Or they could even tell us, hey, infer was wrong here. Maybe this is a false positive. In fact, this is one of the good ways by developing such a feedback loop with developers to improve and get rid of false positives in the analysis. Next, the other thing is that it is very difficult to know how the complexity corresponds to actual perf metrics. To alleviate this, we incorporate some dynamic data whenever possible. If we have some profiling information, we would In addition to the complexity report, we will tell the developer, hey, this function's average CPU time originally was X milliseconds. Another point is to highlight and provide contextual information. For instance, we highlight and provide additional information when code is on a critical path or on UI threads or main thread. We do this in two ways. If available, we rely on dynamic data to tell us if a function is on a critical path, such as an application's call start path, by relying on profiling information. Or we also rely on some static information to look up type information to tell us whether a function could potentially execute on the UI thread. And we observe that when such additional information is available, developers pay more attention to these reports since they may be more critical, which makes sense. Now, you might say, well, if you already have average CPU info, why can you not tune the analysis with that? The issue is that profiling with dynamic information is aggregate, so it is collected over many executions and not all paths are covered. It's only covering some execution paths. But still, it could be possible to use that information for improving the analysis. And there are lots of exciting research and experimentation directions to explore here. For instance, one idea to use dynamic information is for sizes of inputs. If we have a function, for instance, with linear complexity, and if we know that in production it always takes very small values, then we could suppress this complexity increase report since it is unlikely that it would be causing a performance regression. Next, I want to switch gears and talk about two other static performance analysis checks that are worth mentioning. One of them is the inefficient key set check, where we report whenever a developer loops over the keys of a map and also calls and looks up for the value for the key inside the loop repeatedly. Instead, they could get key value pairs and get rid of this extra hash map lookup. This is one of the highest fix rates that Infor gives. And because here the fix is very straightforward, we tell the developer, hey, use key set map. And this is one of the fixes that has been also detected in open source projects thanks to the recent Muse integration with GitHub that uses Infor and reports on open source projects, which I recommend you to check out. The other one is expensive loop invariant call, where you call an expensive function inside a loop where the arguments values are staying the same. So the fix here is to tell the developer to hoist this expensive function call out of the loop. In fact, this analysis was inspired by looking at a serious performance regression on production that was caused by repeatedly calling such an expensive function. First, to determine what is expensive, we rely on the aforementioned asymptotic complexity analysis. So, to conclude the talk, what I want to tell you is that we are scratching the surface here. There's lots of work to be done applying static resource analysis techniques to big code bases in the industry. And with it, it brings new opportunities and challenges. For instance, in such settings, it will be very useful to have an IDE integration telling developers, oh, the complexity of this function you are browsing is ON, or this is constant. Secondly, we could provide developers code search integration functionalities where developers could search for functions that are linear and occur in specific directories. Another promising direction that we are currently exploring is to look at different resources other than execution cost. For example, memory. In particular, currently we are extending the analysis to estimate the size of the objects in auto-release size pools in Objective-C. And finally, we can come up with ways of automatically adding models for library calls or quickly extending the models. So, without providing these type of tools to developers on top of the static analysis mechanism, performance is left as an afterthought that is only faced with when there is a regression. In this talk, I hope I have convinced you that we can take ideas from static resource analysis and apply them to big code bases. And there's lots of potentially interesting and exciting projects to work on. And our focus here is not to be 100% sound and complete, but to focus on impact and help developers catch performance regressions, and other type of issues with performance statically. Our tool is online on GitHub and you can try it. Thanks for your time, and I'm happy to take questions later.